Hello everyone, this is Gopal Sharma. Welcome you all in the csirnet lecture series. This is the lecture 2 of linear algebra. In the first lecture of linear algebra, I have discussed about syllabus, important topics, marks, difficulty level, and what type of problems generally CSI asked from linear algebra. I have discussed all those things in the first lecture. The link of that video is in the description or in the I button. You can go and watch the video. Any exams demands some key things from the aspirant, and those are belief, passion, sincerity, and dedication. If you have all these four things, then you can crack any exams. So today we are going to start our first topic, vector space. So in this topic I have assumed that you are aware of the basic things like definition of vector space, okay, subspace definitions, basis, and dimension of vector space. See, I'm not going to discuss all these things here, okay. Here I'm going to recall some important results which I'm going to use to solve problems. So the first result is if V over the field F is a vector space, okay, and S is the spanning set of the vector space VF, and T is a linearly independent subset of V, and B is a basis of vector space V over F. Then cardinality of the linearly independent set T is always less than equal to cardinality of the basis set B less than equal to cardinality of the spanning set S. See, what does this mean? This means the basis set B is the largest linearly independent subset of a vector space B, and it is the smallest spanning subset of a vector space B, okay. So that means if A is any subset of vector space B, if cardinality of this set A is greater than the cardinality of the basis set B, that means this A is always linearly dependent, okay, because B is the largest linearly independent set. And if cardinality of the set A is less than cardinality of the basis set B, then this implies that linear span of A cannot be equal to the vector space B, because B is the smallest spanning set of the vector space B, okay. So any set A whose cardinality is less than the cardinality of the basis set B will not span the vector space B, okay. So this is our first result. The second result is if W1 and W2 are two subspaces of vector space V over F, then W1 plus W2 is also a subspace which is x plus y, such that x belongs to W1 and y belongs to W2. See, this subspace W1 plus W2 is the smallest subspace of vector space B, which contains W1 and W2. Okay, and this W1 plus W2 is spanned by the W1 union W2. See, the union of two subspaces need not be subspace. W1 union W2 is subspace if and only if one is contained in the other. That means if and only one is W1 is contained in W2 or W2 is contained in W1. Okay. Now the third result is dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. See, that intersection of any number of subspaces is again a subspace of vector space B. And this dimension of W1 plus W2 is always greater than and equal to max of dimension of W1 comma dimension of W2. Okay, and this dimension is always less than equal to minimum of dimension of W1 plus dimension of W2 and dimension of vector space B. Okay. The fourth result is dimension of W1 intersection W2 is always less than equal to dimension of W1 comma dimension of W2, and dimension of W1 intersection W2 is always less than equal to max of 0 comma dimension of W1 plus dimension of W2 minus dimension of vector space B. These are important results about dimensions of sum of two subspaces and intersection of two subspaces. The fifth result is if dimension of W1 plus dimension of W2 is greater than dimension of vector space B, then in that case W1 intersection W2 is a non-zero subspace. Now the quotient space. If W is a subspace of a vector space V over F, then we define B modulo W as V plus W such that this B belongs to vector space B. This element V plus W is a coset of the subspace W, coset of this subspace W in vector space B. Then this B modulo W is called a quotient space, and the addition and scalar multiplication operation is as follows: V1 plus W plus V2 plus W is equal to V1 plus V2 plus W, and the scalar multiplication is alpha times some V plus W is equal to alpha times V plus W. Okay. Now some results about quotient space. First result is dimension of vector space quotient space B modulo W is equal to dimension of vector space B minus dimension of vector space W, and if V is a finite dimension, if V is finite dimensional vector space, then dimension of B modulo W is dimension of V minus dimension of W. Okay, if the dimension of vector space V is infinite and the dimension of W is finite, then in that case the dimension of the quotient space B modulo W is infinite. Suppose if the dimension of vector space B is infinite and the dimension of the subspace W is also infinite, then in that case the dimension of B modulo W can be finite or infinite. Okay, this is all about quotient space.